continue with the deep learning scene and deep neural networks. So we're very happy to have Gérard Ben Arous, who is going to give us a blackboard lecture on the complexity of Tensor PCA.
Thank you very much. Thank you for this invitation. I've never run any algorithm, no, in fact, that's not true. Now it's not much on deep networks, and what I'll talk about here is not exactly directly deep networks. It's about this problem of Tensor PCA, which is a complex and difficult problem of, let's say, statistics, and I try to be a bearer of bad news in terms of complexity. So we've heard, situations where everybody hopes that the situations where the global minimum is the unique critical point, or at least in a neighborhood, things like that. Complexity doesn't bother you. The algorithm will find the minimum, the global minimum, this kind of things. And I'm trying to say that to study cases where this is not the case. So, I start with. So for the moment, I don't have anything to report on deep network, except numerical experiments to show that what I'm saying happens, including in ResNet, so which are purely numerical experiments. But I hope that if we have a conference like this in a year or two, I will have results on networks. So this thing started with the idea that, and this is what I want to say here, that an idea that came from physics, which is that a smooth function of many variables, of n variables, n being large, a smooth random function of n variable can be very complex. Okay? And complex in the sense of it's Morse theory. That is complex, for instance, in terms of the number of critical points, being exponentially large in the dimension, in terms of the topology of the level sets, their Betti number being very large, and this type of things. And so this can happen, right? Which doesn't mean that it does happen for the model you're interested in, but it can happen. And it does, the thing is that it does happen in the case of Tensor PCA, for instance. I'm giving the summary of this in a nutshell. The good news is that there is a parameter, which is the signal-to-noise ratio, naturally, and there is a transition between very complex, but with some correlation with the signal, then simple, and then dynamically simple, right? Which means dynamically simple means the optimization works, all right? And these different transitions begin to be well understood in this model. And in fact, they are. So we've tested them numerically, and they seem to hold in very many places. So let me explain that. So first, this is joint. I mean, this is a big team, and there are people from mathematics, people from computer science, and people from physics working on this. So in mathematics, Okosh Jagannath, who is here, and Reza Ghessari. And in physics, it's essentially, and Andrea Montanari from Stanford, Michal Nika, my former student too. And on the physics side, it's around Giulio Biroli in Paris and his collaborators, Chiara Camarota, Valentina Ross. So let me explain what the story is. So let me start with a mathematical point of view. I could start from a statistics point of view, but so I'm saying a random function of very many variables can be complex, and you don't need to look at a crazy function to do that, right? So what is the simplest function when you teach calculus? It's polynomials, right? So you take polynomials. There's even simpler than polynomials, homogeneous polynomials. Right? Take homogeneous polynomials of n variable, right? Hard to do simpler. Okay, if it's degree 1, this is a simple function. If it's degree 2, it's still a simple function. But if it's degree 3 and above, it's a very complex function. All right? So of course, this depends what polynomial you take in. So take a random homogeneous polynomial of degree p in n variable. Right? So how do you choose random? Choose its coefficients to be random. IID. Right? Gaussian, for instance, if you want to take that as simple as possible. All right? This function is a mess. You take such a function, you can use whichever computing power you have, you will not find the minimum of this. All right? So that may be a surprise. So this function, of course, is interesting. So let me write it. And so typically, because it's homogeneous, you can restrict it to the unit, to the sphere. Right? It's homogeneous, of course. You can look at it on the compact manifold, which is the sphere. All right. So now we have a compact manifold. Typically, such a function is Morse, which is Hessian is never degenerate. So you can, it has a finite number of critical points, and you can count how many. And this number of critical points is in fact exponentially large in n. The number of minima is exponentially large in n. Right? And you can have many more, much more detailed information. It's a long story. So this is a very complex function. And again, the story, the link with this function comes from physics, in fact. The idea of looking at this for physicists, this is called the spherical p-spin. This is the Hamiltonian, it's an energy. And the physicists tend, for whatever reason, I keep their notations here. Instead of taking the sphere of radius 1, typically we will look at the sphere of radius square root n. Makes no difference, except that you'd better fix this because the nightmare in this thing are the normalization. So let's fix one normalization. And then so the function I'm looking at is just something like this. Right? And you choose these guys to be independent in 0, 1. Okay? And for whatever reason of normalization, you choose, you normalize by n to the p minus 1 over 2. All right? All these makes no difference, of course. This normalization, np over 2, if you put it there, this would bring you back to the unit sphere. Right? And then you have the square root n left here. But whatever. So that's the usual normalization. So let me remind you what this is. This guy, of course, you can look at it as a Gaussian field of the sphere. Of course, this h of x is a Gaussian field, Gaussian function, if you want, a Gaussian random function. And its mean is 0 here. And its covariance is, just an easy computation, is the overlap, as the physicists call them, which means simply the inner product, here normalized by n, because this norm is square root n, to the p with an n in front of it. Right? So the important thing in this covariance structure, that's easy to compute, of course, it's just a one-line computation. This covariance is, the variance is fixed, the variance is n. Right? When y is x, this is n. So the typical fluctuation, the mean value is 0 for this thing. The typical fluctuation are square root n. And the important thing about this covariance is this is an isotropic field. Right? It's invariant by rotation. The law only depends on the distance between x and y. Here about they only depend on their angle, which of course on the sphere is the same thing as the distance. All right? So this is a very simple field. But you can forget this side. You can just say I take a random function, a random polynomial. And the story that this thing is very complex, and I will say more about that. Okay, and this started because with Jan Lecan a long time ago now, 4 years ago, when I mentioned, but the landscapes, landscapes of statistical data science or deep learning are, in fact, in the end, you build, as we've seen, you build a loss function, which is a function of a parameter which is usually in very large dimension. which is usually not exactly smooth, or LU is not smooth, but we all do as if it were smooth, and where which is random. The randomness is a little different because the randomness comes from the sampling, the fact that you have your loss function is usually the empirical loss function, but it's a random function of very many variables. So why aren't they complex? And so why is there any hope that minimization will bring you to anything like the global minimum? Right? So, and then this is where we tried, and his group at Facebook tried to minimize this, and of course failed, for a very good reason. You simply cannot find the global minimum of this thing in finite time. So that's one example. This function is terrible, and I will say more. So maybe I can say what we know. We know at least you can find that the number, if I call crit, the number of critical point of this function, of u, this means I look at here the number of local minimum, or of critical points below a level, let me write this so that it's easier, negative nu, below this level, so that's a deep level. I remind you the typical value is 0, the fluctuation are square root n, then in fact the absolute minimum is of order negative constant times n. Right? So you're looking at very deep values. The number of critical points at this level behaves exponentially, a certain function depending on u, which can be explicitly computed. This was done in a long time ago now, 5 years ago, by Aufinger, in a series of 2 papers with Aufinger, myself, and Czerny. And you can give much, much more detail than that. You can also compute the number of critical points of fixed index. So for instance, if you take k equals 0, you're counting the number of local minima. You can compute the expectation of the Euler characteristic of the level lines, right? And look at the topology of these things. You can understand many, many things. So that was done there. This you could still say, but yeah, but that's just the that's just the mean. So it might be that the true number of critical points doesn't behave like this. But for you low enough, for you very low, the second moment has been computed. So if I put this, it will be there. And this behaves like twice the first moment. This is due to Subag, Eliran Subag, who is now a postdoc at Courant, but was then a student at Weizmann. And using this, you can deduce a lot of things. You can prove that so this is really, at the bottom of the landscape, there you can compute, there are exponentially many local minima. You can really prove where the ground state is and this kind of thing. You can understand the structure of the extreme values. You can understand the structure of the Gibbs measure, temperature chaos, and all this kind of thing. So there's a lot of papers continuing here. There's Subag, a very important paper, Subag in 16. And if you want the last on this, there's a paper by Subag, Zeytouni, and myself about all this story. But this was started really by this competition of Subag, who was then a PhD student. So this function is very, very complicated, and let me explain it with a picture what it does. So here you have the level 0, which is the level of the mean of this function. Typically, the natural fluctuation over size square root n. Right? And the ground state is at a level here, which is at negative, I call it E0 n. Right? So the ground state is there. The absolute minimum is there. And now there is another level here, which I call for whatever reason E infinity times n. And this is what the physicists call the threshold level. At this level here, at any level between this and that, you have an exponentially large number of local minima. Right? So the situation is terrible. Above this, you have no local minima. The probability to find one here is like exponential minus n squared. So they are really all here. The local minima here are the most numerous. Here they are very rare. You have only very few, and they are the deepest one. Here they are very thin. Here they are pretty broad. right? And what happens here, so that's the structure of the complexity. If you try any kind of dynamics to try to find the ground state, which is here. So you should think there are a few guys like this. Here you have an exponentially large number of wells, like that. Right? And when you want to go down, you have to cross extensive barriers of size n. So the time to cross them is exponential n. Right? So you can imagine that the mixing time, if you take now, let's say, Langevin dynamics, right, which you'll see what it means. You take the gradient dynamics for this function, and you add Brownian noise on the spherical Brownian noise. So this is the natural dynamics for this thing from a physics point of view. The time to reach equilibrium here, when the temperature is pretty low, will be exponentially large. Right? That's a result which is, so the mixing time is exponentially large at low temperature. Exponentially large in n at low temperature. And this is a result which is due to Reza Ghessaei, who's still a student at Courant, and Ukosh Jagannath, who is here. Who is at Harvard, I'm sorry, but sitting in a room. And this has been extended recently by Ukosh Jagannath and myself to more, let's say, more detailed statement that I don't want to get into. But so, if you take a low temperature, which corresponds, let's say you want to go to this level, and you start from a point taken at random on the sphere, you start from here. And the time to get there will be exponentially large because you have to cross all these things. Okay? And of course, if you did any kind of, try whatever dynamic, crossing this will take a long, long time. Right? So it's natural to predict that in shortish time, you might get here or just slightly above here if you start from a typical point. Right? So this phase of shorter dynamics, shorter time dynamics, has been studied by physics. It's called the Couglien-Dolocourt-Chan equation, and has been established mathematically rigorously by Alice Guillonnet and myself, and Amir Dembo 12 years ago, I think. All right, so that's the picture for this thing. You try any kind of reasonable local dynamics, and you will get stuck probably above this. Right? And this is what happened when Facebook tried. They found but there's something to be remarked. In short time, it looks like you can get to a depth which is negative constant times n. So it's already deep, right? Because the typical points are depth square root n. But you cannot get to the real deepest dive. Okay, so that's the story here. All right, let's take another polynomial. That's not true for every polynomial, of course. Let me take another polynomial, which is just the polynomial which would be, and I fix, let's say, x1, first coordinate, to the p. Right? This one is not complicated, right? So if I draw the sphere, if this is the axis 1, then I have this function, is, of course, the sphere in dimension n is, this is a poor caricature of it, but so this function, of course, has a minimum and a maximum at the north pole and the south pole, and that's it. Right? Of course, it's not a Morse function. The situation on the equator is, of course, the gradient is 0 here on the whole equator. But in terms of minimum and maximum, that's a simple thing. Right? So, but of course, this one is not exactly a random polynomial of many variables. It's in fact a function of one variable. Right? So now here is a mathematical question. What about if I add this one and this one? If I mix them, right? Let me call this one H1. What if I go look at H? Let's call this H0. What if I look at h of x, which would be h0 of x plus, okay, with the right normalization here, it should be this. And I guess I have the square root n here. And I put a constant lambda. Right? So when lambda, so lambda is like a signal to noise ratio with a proper normalization here. Right? This is just what it should be. Okay, so if lambda is 0, this function should be very complex. We know because that's the other one. When lambda is very large, this signal should say something. And in between, something should happen. Right? So the question is this, first there are many questions about this. I give you this landscape on a very simple manifold, which is the sphere. First question is completely geometric. Can you understand the topology of the landscape? Right? Is it a complex or not? Second, of course, is what we had in the former talk. Optimization was a question mark. Same question. Can you find what happens if you do whatever kind of dynamics to find the algorithm to find the minimum? Will you find it? Where will you stop? Right? So we saw here that when there is no signal, you stop very far from the global minimum. Okay? So that's an interesting math question. Okay, why would we want to study it? So let me forget everything I've said up to now. And so that's the way. Of course, I will give the answers to the question I just raised. So why is that a decent and interesting problem? So let's go to Tensor PCA. Right? And of course, Tensor PCA is exactly this problem. So what is that? You imagine that you have a tensor. And so PCA, of course, for matrices, of course, remind you what that is, principal component analysis. I give you a matrix, and I try to, let's say, maybe a simple matrix, maybe a rank 1, a rank 2, a rank 5 matrix, and perturbed by something random, say Gaussian. And you observe the noisy version, and you want to find the, let's say, rank 1, 2, 3, 4, 5 matrix that is behind it. Right? And that's the absolutely first thing you do in statistics. Right? So when you have very large random matrices like that, perturbed by a rank 1, or let's do the simplest case, a rank 1 thing. So can you detect the signal in a random matrix? The answer is it depends. Right? And so there is a transition, which is well known. So in the case of matrices, the question is the following. Let me give you normally the important matrices are typically covariance matrices, empirical covariance matrices. But let me present that in the simplest possible case. Let's imagine that you have a random matrix. You observe a matrix M plus a rank 1. What should I call that? I don't know. U, and this is a rank 1 matrix, right? Symmetric matrix. Let's say U is just little u transpose U. And you observe this, and this one is, say, Gaussian. So you observe this matrix. Right? And you want to understand, of course, you have to normalize everything properly, but you want to understand Gaussian symmetric real matrices. You observe that, and you want to know whether you can know U. That's the problem 101 of statistics, right? And in this problem, you have two things. First, can you detect? Second, can you recover? Right? So detect means you observe this guy. Can you detect that there is a signal? That this, what you're seeing is not simply completely a random matrix. Right? And then if you detect that there is something, can you recover? Partially, completely, this guy, right? Which is essentially one vector. All right? So this is well understood. This is a problem in random matrices. You look at the spectrum of this. This is a GOE matrix, as physicists would call it. So you know the spectrum of this. The spectrum is a semicircle. That would be the spectrum of this thing with pure noise. I mean, with no noise. No, with pure noise, I'm sorry, no signal. And now the question is what happened depends on the strength of lambda. So there's something which is called the BBP transition. I'm sorry to quote myself here, but that's how it's called. So this goes back to 06, and this is Jean Hobike, this is Sandrine Péché, and this is myself. So when lambda is too small, you don't see the spectrum is unchanged, and there is no way to detect even that there was a signal. And when lambda is large enough, then you see an eigenvalue that will come out of the spectrum, and the eigenvector of this guy is not far from the vector that you want here. The larger the lambda, the closest this is. So what you do here is you recover by taking the eigenvector, you recover partially, and the larger the lambda is, the better you recover. Okay? So this is this transition here. That's very simple. That's the problem of random matrices. In case of tensors, there's nothing like a spectrum you can compute.
Question. Why do you look at with this motivation GOE rather than the Wishart?
The initial thing was done in the Wishart case, but you will see why you do the GOE.
But then it's a different condition?
No, it's the same. I mean, the values are different, but okay, the Wishart case, you see this thing, right? That's my rendering of a Wishart density, and you have something like that, and the transition is perfectly. I mean, there's a huge literature on that after this, really, very long, and you can do that with more than rank 1. You can study what happens in the critical window. Everything is understood here, in fact. You can study what happens when this matrix is not Gaussian, but that's not the. I'm interested in this picture. You'll see why in a moment. All right, so that's the case of random of matrices, the usual PCA. Tensor PCA is the same thing. So it's also called spike tensors. Right? So tensor PCAs, you observe let's say rank 1. So you have a rank 1 tensor. Of course, you ignore who V is, because otherwise the problem would be simple. And you observe this noisy version of it. This is a Gaussian tensor. Let's say with IID component. Right? And the question is, can you detect and can you recover? Can you recover weakly? Can you recover strongly? And all this might, of course, depend on the strength of the signal-to-noise ratio. Right? All right, so I assume this to be Gaussian, and I put a prior on my, in fact, I put no prior, essentially, on my V, just that V is of norm 1. I'll just say that V is, I know nothing on V except, let's say that it's known. Right? So with this, what can you do? I don't know. I don't know enough statistics, but the only thing you can reasonably do is maximum likelihood. Right? So that's easy. If you try to find the maximum likelihood estimator of this thing, right? This is Gaussian. You have a spherical prior. You could, of course, take a non-spherical. For instance, you could also study the prior to be on the vertices of a hypercube. Right? That's also a very interesting problem, and there is interesting recent work by Wei Kuo Chen on that. But I won't go there. I take this simple smooth prior. If you do the maximum likelihood estimator, then you have to maximize the log likelihood. Let's put a negative sign. You have to minimize a certain function. Right? The function you have to minimize is exactly this. That's exactly the same problem. Except, of course, that here I put myself on the sphere of radius square root n. So this square root n annoyance is just to make this coincide with the physics literature. All right? Why do the physicists work on the sphere of radius square root n? Because in fact they think of the spin glass first on the vertices of a hypercube. So if you take the vertices of a hypercube, of course the norm, which are plus or minus 1 to the n, the norm is n, the norm squared is n, so the radius is square root n. That's all. Okay, so just do this. It's a 1 minute computation, and this is what you have to do. Right? So understanding this is, in fact, solving the tensor PCA problem. All right? So how do you do that? So let me just say that in words. How do you compute? So let's try to first understand the complexity of the static complexity, which might be completely irrelevant for the dynamics, by the way? We don't know. But let's understand the complexity, the geometry of this landscape. So how do you do that? There's a method for that, for the So the complexity of the spike tensor, of Tensor PCA. So the method, of course, is the Cass-Rice theorem. So Cass-Rice goes back to the 30s and beginning of the 40s, and it's a formula that allows you to compute, that's exactly what was done in the case of the spin glass, allows you to compute the expectation of number of critical points below a level, whatever, of this function. Let's say below a level minus nu. This can be computed, this expectation, I won't write this in detail. This is computed in terms because everything is Gaussian here, in terms of the distribution of the absolute value of the determinant of the Hessian of this function, conditioned by the fact that the point is critical, and maybe by the level. Right? So you have to compute that, the absolute value of the determinant of a Hessian, once you have conditioned by the fact that the point is critical, stationary, and maybe by the level. Right? But this is, of course, a random matrix. The function was random. This is a random matrix. Real, symmetric, Gaussian. When you condition by this, it becomes, and so if you have no signal, like I had before, this becomes a GOE. And with this condition here, it becomes this semicircle shifted by something which depends on you. That's why I wanted the semicircle. So this tensor PCA thing, through Cass-Rice, reduces to a problem of random matrices. But now what happens for the case where you have a spike? It becomes now a GOE spike, exactly this. So in order to compute this thing here, the PPP transition is not enough. You don't simply need to know that there is an eigenvalue getting out or not. You need a little more than that. You need the large deviation result for that. When you do the case of the pure p-spin, you needed large deviation for a random matrix spectrum, and this had been done in the 90s, at the end of the 90s by Alice Guillonnet and myself, and 20 years ago. And here, for the case with the spike, it has been done by a student of Alice Guillonnet, Mylène Maïda, 10 years ago, I think something like 7 or 8. And so you have the large deviation principle for that. Right? So once you understand really the large deviation of this behavior of the spectrum, you put all that in this thing, and you can compute this guy. Okay? And so this has been done rigorously by, in a paper by, okay, I'm sorry, it starts with me here, alphabetically. Montanari, no, May, who's a student of Montanari, and Nika, who was my student. Okay, so doing this, you can compute this first moment. And in fact, if you want to go deeper, this one cannot move. There's a much more detailed work to compute the quench complexity. Because this, as you see over there, is the anneal complexity. It's the first moment. If you really want to compute the complexity, there's a more recent work by myself, Camarota. Oh, I'm sorry. Biroli, Giulio Biroli, that's and Valentina Ross. Where there we compute the quench complexity. So the equivalent of what Eliran Subak did, computing the second moment, but here we compute really the quench complexity, except that we use the methods of physics, so it's still in need of a rigorous proof. I mean, for a mathematician, but it's the truth. Anyway. So, like always with these guys. So it's a great thing. So, and of course, to do that, we use a kind of weak form of the replica trick for the computation of the complexity. Today, of course, you just brought me a croissant in a bag with, on it was written replica. So when you go to Montreal, you find a replica croissant. So here you have a replica computation complexity. If somebody wants to put that on firm ground mathematically, you're very welcome. There is room here. Anyway, so what are the results? So let me do that. I mean, we have many theorems, but let me do that with a picture. Okay, so I have this function depending on lambda, and here is my sphere, and here is the signal, which is the North Pole. Remember, we don't know where the North Pole is. We don't know that the signal is at the North Pole, otherwise everything would be simple. Remember also, this is a sphere in very high dimension, so essentially every point is on the equator. Right? Being far from the equator is extremely difficult. The whole mass is here. All right? Now, so when lambda equals 0, we know that, so we are essentially, everything happens on the equator. We have an exponentially large number, or near the equator, exponentially large number of critical points. This very complex landscape I was describing happens on the equator. Right? So you have very deep minimum, you have the threshold, whatever. So you have, let's say, a little band like this around the equator, where here you have exponential complexity. And the absolute minimum is somewhere there. The threshold states, which are very numerous, are also there. Right? So when lambda begins to increase, lambda increases this way. In fact, exactly like in the, this is not very spherical. So exactly like in the matrix PCA, the BBP transition, for a while, it stays like this. So for a while, you still have the complexity like this, and nothing happens related to the spike, right? So this is until a certain value, which is called lambda IT. So by the way, if you want good literature on the Tensor PCA, there are very nice papers which are now going back to 2014 or 15 by Andrea Montanari and Richard, in fact, and Montanari, Reichmann, and Zeytouni, where they use also the result of Ofinger, Charney, and myself to do this first analysis. And there are also very, very interesting paper by Bandera, my colleague in Courant, and Perry and Wine. Anyway, so that's where you see the introduction of this information theoretic threshold, which says below this, you cannot detect, right? Even if you could minimize whatever you want, the landscape is like that.
Can you explain just again what was the shaded region?
That's the region where you find the complexity, the local minima, all the critical points. All of them, right? And you have an exponentially many of them. Then at some point, okay, this is less and less spherical. Then at some point what happens is you have, you always keep this exponential complexity at the equator, right? But at some point, so maybe this could be a bit wider, I don't know. At some point appears a band like this, right? Where you have exponentially many minima here. So this is nice because this says that a priori maybe here you can do weak recovery. You can find one of these, right? You are correlated with the signal. And then even later, you always keep this exponential complexity here, but now you have only one local minimum very near the thing here. So this is, of course, in the former talk, we had this condition when all the norms were smaller than 1, you had a unique minimum. So here, if I tell you that, if somebody told you that things are happening in this northern hemisphere, then things are simple. Right? But you don't know where the northern hemisphere is, of course. And then, of course, the more lambda grows, the more this thing comes close to that. Okay? So that's the landscape.
There is no lambda where it becomes.
No, you can prove that it goes to 1 and you can control in terms of lambda. Of course, it's that thing. So, so that's the picture. What is now happening? So that, you have very complex, hopeless, something intermediate, and something simple. Now, yeah?
Can you elaborate on what happens as lambda increases?
Yeah, I'm just going to do that.
Okay.
So here it's already a lambda finite when this happened, right? In my notations here. And it will be, if you let this lambda go to infinity, this critical point will come to the top thing here. You will always keep this exponential complexity here, of course, because if you sit on the equator, this term is 0, right? If you sit on the equator exactly, you'll see the complex function we had before. Losing one dimension in dimension n, which is 10 to the 6, doesn't make much difference. So you will still keep this exponential complexity. But now the question is, what about optimization? What about finding this guy? Right? So as I said, so you can try many things. But let's try the natural thing to try for. So you could look at gradient descent. You cannot really look at stochastic gradient descent here, and at least as I presented it. In fact, you can, but you have to change this a little bit. But here I gave you one picture of this tensor, only one, and I say find the true rank 1 tensor, which is the North Pole here. Right? Of course, I could give you a sequence of such pictures, and then you try to learn the North Pole. And there you could do stochastic gradient. We also have results for that, but I will report that later. So let's try first with what happens with Langevin dynamics. Right, so you do the natural things here, which is, and if you want, you can of course also study pure gradient descent. You won't go far with that. And so, of course, Langevin dynamics consists, as I said, as following on the sphere. This would be a Brownian, a spherical Brownian motion, and you would have here minus a constant, whatever, beta gradient of my function h. Right? So, as I said, of course, you know that this thing will go because this is a reversible dynamics, and the invariant measure is the Gibbs measure, exponential minus beta h lambda. So you know that this thing in long time would converge to this measure, which will be, when beta is large, concentrated on very low values. So that would be, you know that this works. Right? Except, as we saw, the mixing time, at least when lambda was not there, can be exponentially large. So you're not interested in the long time dynamics of this, you're interested in the short time. Right? So what we see is the following. So there is no, maybe I should, first there is no known algorithm that finds the signal in finite time, or in polynomial time, when lambda is finite. Okay? It's impossible, at least for the most part. Right? So the best known algorithm is an algorithm which is not at all a minimization, an optimization algorithm like that. It's a spectral algorithm. And it works, so the best known, and I'm not even sure there is a proof, but I think so, algorithm is spectral, and it works. And works when lambda is of order n to the p minus 2, with this notation to the p minus 2. There is no way, nothing works, nothing is known that works when lambda is smaller than that. So in this regime, it means you've been in this space for a very long time. Right? It's a very simple thing. So there's this huge region where the landscape is simple, but you cannot find it. Right? So what's the reason, of course? It's because when you start, I mean, it depends. You can find it if you start in the hemisphere, if you have a hot start. But you cannot find it if you start with a random point. So when you start with a random point, you start near the equator. When you start near the equator, you have to find the entropy. You have an entropy, a free energy barrier. And to cross it takes a huge time, except if the signal-to-noise ratio is large enough. Right? That's not what this algorithm does, but any variant of gradient descent, stochastic gradient descent, will have to solve this, or Langevin will have to solve this difficulty. So what we find here is the following. So this works. So the Langevin dynamics finds the signal in finite time. And when I say finite, it's really finite. It's not finite, but very large. When lambda is of order n to the p minus, let's start with this, p minus 1 over 2. Right? Started from essentially any point. So what happens here, so let me explain that. Okay, good. So this is a result of a recent work by Gesari, Jagannath, and myself. So here's the story. You start, let's say, from a random point. In fact, you could start from other points. So you're near the equator. When you sit at the equator, if the signal of the North Pole is where, for me, where the camera is over there, and here I have the whole population of the sphere, keeping me here. So what happens is that there's this kind of hill I have to cross, entropic barrier. When you start with, when lambda is like that, you are, in fact, the hill is behind you. So you just have to go downhill, and you find the. So that's what happens. Right? So in fact, you don't have to cross this hill. So that's a very uniform result and a very complete one. Then, so let me explain that. I mean, you may think, yeah, but Langevin dynamics is for dummies. That's not that true, because in fact, the other algorithms that are known, approximate message passing for this kind of thing in other contexts, or tensor power iteration, also work provably when lambda is of this order or larger. So Langevin dynamics, which is like the optimization for the poor probabilist, still works exactly. Yeah.
So what are the critical values of lambda of that picture?
Don't ask me. They are explicit,
But in terms of n?
Oh no! Here they are finite. This is finite. So that's what I'm saying. There's a huge room when this happens. Lambda is 17, but we have to do something to find this. So there is this whole region between lambda equals 17 and lambda equals n to the power whatever, where you cannot find this. So there's a huge room for improvement, right? Now, what we can find also is something a little better. So now if we take lambda, which is little o of this, so if lambda is less than this, then there are bad points, bad initial points. Let me not explain too much about that, but I can say just a few words. So when lambda is not as strong, then you cannot start from any point. There are some bad points. Because of course you start from something, let's say, near the equator, and some of these points are bad. And you will not correlate. Here we can prove that you will not correlate in very long time. Okay, exponential square root n time or something like that. Right? So you have to be a little more prudent. So, but the fact that there are bad points does not prevent a typical point to be good. Right? So in fact, we prove that when lambda is of order n to the p minus 1 over 2 minus constant, eta, and I call it eta because it doesn't go to 0, it's 1/4 or something like this, so a little less, then the Langevin dynamics find the signal, or correlate to the signal, in finite time, when started from a typical point. So point chosen at random, which is a distance here with this normalization 1 from the equator. So this is important. This says that we are beating the best things even with clever algorithms. It doesn't mean that the algorithm beats it. It's just the proof beats it because Langevin is probably easier to analyze. Right? What is believed is that this is true until lambda is of order n to the p minus 2 over 2. Right? And there it should break. Right? So between p minus 2 over 2 and 0, I mean, the finite thing, we don't know what to do. So what is happening here is interesting. Let me explain, if I have still a little bit more time, what's going on. So when you are in this regime, you have this hill. So the equator is behind me. North Pole is there. I have this entropic hill, which I have to cross. The only thing that can help me cross it is the gradient of the term with the signal, essentially, or the gradient of the noise, which could be exceptionally helpful. Right? Because the gradient of the noise could also point in the right direction by chance, and strong enough. Right? So in fact, what we see here is this happens. You have exceptional point in this barrier, which we have called equatorial passes. For an obvious reason, this is near the equator, and you have this mountain, and there are some passes. And the question is, if you start from one of these passes, or if you start near one of these passes, you can find it and then go down the hill on the other side and go to the North Pole. But what is going on is that, so you have this in front of you. Behind you, you have the hell of mediocrity, right? Everybody else wants to pull you back. Entropy is pulling you back to being like everybody else at the equator, right? So it's pulling you back much, so you have like an absorbing thing. Either you reach one of these passes before you're swallowed by the equator or not. And so when you are in this regime, you find one of these equatorial passes fast enough, because there are enough of them. Because when lambda is large, what you ask for the spin glass term, how you ask it to help you is not very good at constraining. But of course, when lambda will be smaller than this, you're almost sure that the equator will swallow you before you find one of these, right? So that's the story in words. Of course, it's a long. You see here, it's not a question of cat's rice of understanding complexity. It's a pure question of understanding dynamics in a random landscape. But so this, in fact, this barrier is serious. Let me explain a bit.
Just to confirm, the spectrum is at p minus 2 over 4.
What? Yes. And we have no way to get there.
And in your story with entropy, field, etc., how does spectrum fit in that picture?
No, again, this is large, so what the complexity tells you that as soon as you're a lambda which is finite, large but finite, this guy is already completely isolated. Right? So you have no way to get into these phases.
But it is an efficient algorithm.
It is an efficient algorithm, but only there. In fact, I just mentioned that because that's the best known, and it's still very bad. You could imagine that you could do it with lambda finite. In fact, you cannot, because there's a theorem saying that finding something in polynomial time is NP hard. Right? So.
What? No, but not for random.
I'm sorry?
Not for.
Yeah, I understand, but it tells you be careful. Right? So that's why, otherwise I would not even say that this is an interesting problem. I don't know what the solution is, if there is something or not. But I'm saying, even if the smartest algorithm cannot do lambda finite, and far from it. Right? Now, what is... so let me explain in a few words, if I have a little bit of time. What happened, so that was Langevin, which is gradient descent, noisy gradient descent. Okay? And I give you one picture. With this, you build the landscape, try to minimize. What if I give you now K pictures? Right? K realization with, of course, the same signal. The signal changes. Right? So what would you do? One way to do something is the poor man thing is you just take all these pictures, and this is stupid, you do a batch of size, the whole thing. This, of course, reduces the variance of your noise, which in some sense increases the signal-to-noise ratio, and you apply this, hoping that your signal, if you take enough K, your signal-to-noise ratio will be, the signal will be large enough, and you can have a chance to do something. All right, that's one thing. But then you could also say, no, I can do stochastic gradient descent in this case. Right? That is, I have one picture, let's say with batch of size 1, and anything in between. So I take one picture, which gives coming with some noise, right? The signal plus my, and then I follow the gradient of this, then I follow the gradient of the next one, and so on. That's stochastic gradient descent, right? So in physics term, this is called annealed dynamics. In physics term, it's my Langevin dynamics, if you want, but in a situation where, I mean, you follow the gradient, but you're in a random landscape, but the random landscape is renewed at every step, right? So that's very good. Why? Because of course, the bad things of your, you know, or maybe the good things, the passes that you have in this equatorial thing, change at every step. So maybe you have more chances to find them, right? So if you do that, in fact, you find that once you, so this depends on the length of how many pictures you have, but once you've reduced everything to the signal-to-noise ratio, this stochastic gradient descent works until this threshold and stops working there. Right? So if you do that, of course you have to convert in terms, because I just want to give you something you can compare. If I give you K pictures, K that being large, then it's better to do one by one stochastic gradient descent than to pool them and do what I did before. Right? So in this case, of course, why is that? Because what I'm describing here, the stochastic gradient descent, is like the noise only comes from the randomness of the spin glass term. You don't add noise. If you look at the overlap with the, or let's say the inner product with the coordinate x1, with the North Pole, this evolves like a diffusion in dimension 1 in a potential well. And the potential well is like this. So it's a dimension 1 thing, right? I'm looking at the angle with the North Pole, or this inner product. You start from 0, essentially, right? Because you start from the equator. The North Pole is at 1, that's where we're at. And it's like a diffusion in a well which is like this. So you have to cross this barrier, and then you end up here. Right? When your signal-to-noise ratio increases, this guy comes closer to 1, and this barrier becomes smaller. And so at some point, the point where you can cross is this. All right? So this tells you something really strange is happening, because you have this region where you cannot do anything. So why is that? And then we'll finish with that. That is because, in fact, in this context, because there are many other contexts. For instance, take the example, if you don't like tensor PCA, take the example of a mixture of two Gaussians. Right? And you want to understand that. Let's say same variance, identity, and the mean differs. Right? So there are results by Montanari, for instance, showing that in the right regime, this model is simple. Simple in this sense. You have a unique critical point and so on. But there you also have something that plays the role of the equator. It's a separatrix between the two bases. Right? And if you look at what happens, so that you have the equator, like here. Here the whole problem, the whole hell, comes from the equator that you cannot escape. But in this problem of the mixture of two Gaussian, it's simpler. Why? Because at the equator, what happens here, why it makes this thing is so hard, is that at the equator, the function is x1 to the p larger or equal to 3, so its Hessian is 0. It's flat. So the function cannot help you escape this, right? The signal. The signal has exactly 0 influence at the equator because its Hessian is flat, right? And that's why you have to beat the entropy, and it takes so long, and it takes such a large lambda. Whereas imagine that you had here a situation where at the equator, you had a Hessian that helped you, that pushed you away from the equator for the signal. Then maybe this would not happen. Right? In fact, that's the theorem. If you take this example, but now you take your signal, your noise to be the p spin, p equal 3 if you want. But now you take the signal to be x1 to the power 2 instead of 3, right? So this one will have a Hessian that helps you. The Hessian doesn't vanish at the equator. So the Hessian helps you get away from the mediocrity where everybody wants to be, right? And then the lambda you need to find the signal is much more smaller, right? This is, for instance, what happened in a mixture of two Gaussians. There you have a curvature that pushes you away from the place of maximal entropy, right? And this helps tremendously. Okay? Of course, you could even look at the case where p equals 1, where the signal is super strong, right? So you have the p spin and x1. There, not only the Hessian helps you get away from the equator, but directly the gradient of the signal helps you. So that's even much better. Not surprisingly, this was the case studied for 40 years by physicists. Because p equals 1 corresponds to the spin glass model with a magnetic field, right? And we know that when you have the spin glass model, which is a pain in the neck, if you add a magnetic field strong enough, you get away from the difficult region, right? So that's what I'm explaining. So this understanding works in other contexts, and the best example is the mixture of two Gaussians, where you have the same thing. You know, look at the paper in 2016 by Montanari and his collaborators, and you will see exactly this picture. You have an equator which carries all the mass, but you can get away from it when the signal gets stronger, and then you don't need such a strong signal to find to correlate. Okay, so I'll stop here.
I have a question. You mentioned the case where you have multiple images of the same, multiple, let's say, random drawers
Yes,
of the same
yeah.
function, right? And one of the pieces of intuition you shared is that this might increase your chances of going through this entropic field by finding those passages, right? And is it clear how that compares to doing multiple restarts in some sense of those iterative methods on one image?
No, I see your point. Of course, it's better to have more images than multiple restarts, for a simple reason that, you know, these multiple restarts means instead of starting from one point, you're starting from many points. So you're in a regime where this doesn't work, where you don't find easily such a pass, and you say, maybe if I start from many, many points, I will be closer to one of those passes. And yeah, but in this regime, the passes are rare. So probably, I don't know, we've not done this computation, but Okosh is just behind you, so I'm looking at him here. You probably would need an exponentially large number of such starts to be close, depending on the regime. I cannot compute all these normalization, but to be close to to be close to a place where you can find one of those passes quickly. Agree? Okosh, would you? Yeah.
And one more quick question, if I may. Regarding the discussion between Wishart and Wigner at GOE and GUE, so what you described here is I get my outer product, I have my signal, right? And I take the outer product, and then I corrupt this with Gaussian noise, right? And that is modeled by the semicircle distribution, right? So would I need the other kind of distribution if I were corrupting my vectors to start with before I form my tensor? Is that the difference?
I don't think so. But let me explain. Okay, since you're bringing this, well, that is cool and nice, but it has nothing to do with deep learning, right? Directly. It's data science, but it's not deep learning. So what we're doing now is look at, and I promise it would be done in a year or two. Maybe I'm ambitious here, but if you look at a model where you have layers like this, and you have, let's say, the simplest model with maybe one hidden layer, then it looks like what will come, the random matrix that will come from the cat-sparse analysis will be a very complicated modification of Wishart. So, which is there is justice in that, because in the free probability world, the GOE is the Gaussian variable and the Wishart is the Poisson. So in some sense, that's the example we find. But this is still, this will need a lot of work. But I agree, in the end, it will be Wishart. I mean, I'm almost certain that for all the important models, it will be Wishart. By the way, I didn't mention, let me mention very quickly what happens for, so there's this other paper with Biroli, Marco Basie, and Levin Sagoon, who was a student of mine. Basie is a postdoc of Biroli and many others, where we analyze numerically 4 networks to compare this to the glassy dynamics. So in physics, we understand very well what the glassy dynamics produce. Very long period, aging, things are stuck for a long time. So for instance, if you take the pure P spin and you look at the dynamics, what will happen is that you will, in short time, because if you get long time, you will cross the barriers, but in short time, you will get to this, essentially the threshold, or maybe a bit above it. But what you will see is that essentially your diffusion will wander around, finding nothing interesting, then begin going down the level as a power, and then will stop. And it will stop essentially at this threshold or above, which is not the ground state, which is not the absolute minimum. Now you can try the same thing. So we've tried that on different networks. One, a toy model with one layer, on realistic databases, the ones everybody uses, CFAR 10, 50, whatever. And more and more complicated such things, and to end up with ResNet. And what do we find? We find exactly the same thing. That is, it looks similarly initially. It starts by just going around, going down, in fact, at a power which is slower than glassy, and then stopping. But the difference, of course, is that it stops at the level which is essentially the absolute minimum in those networks. So it's not this threshold thing, right? And so, of course, this threshold thing happens when you have this complexity or this complexity, right? Not here. Here, the difficulty is to escape. But then when you converge to something which is the minimum. So then we wanted to compare. There are ways to compare with the physics answers by computing what is called the response function. And then we see that essentially it's not glassy, except if you make it glassy by the following thing. Take a one hidden layer thing. If the dimension of the inner layer is large enough, so of course we have no theorems for that, right? What I'm saying is purely numerical. If the inner layer is large enough, right, so larger than the intrinsic dimension of the function you have to learn, then you are essentially, my understanding, that you are in the simple phase, and you find the minimum. But now to put it in the complex phase, what you can do is reduce this dimension. And then when you do that, you find exactly the glassy behavior. That is, this thing goes down and stops at a level which is like the threshold, way above the true global minimum. So of course, this means that in realistic systems, if you try to do that and you're on Facebook or Google or whatever, you just increase the size of the inner layer. You avoid complexity. Right? So, but in fact, it does exist. In fact, if the function you're trying to learn is just too complex for the layer you want to put, then you stop at the threshold, which is not the absolute minimum. Okay, and you stop and you age. If you gave this system exponential n time, you will see exactly the aging of a spin glass.
Okay, we should stop here. I'm sorry, I take the rest of the question on time because we're on the tight schedule. So let's thank Gerard again.